Hey everyone, today we have another video in the Hugging Face Practical Guide series. Today we're actually going to be taking one of the pre-trained Hugging Face models and fine-tuning it on our own downstream task. If you don't know what the Hugging Face library is, then check out my last video on the basics of the library. And if you guys have any questions or you don't understand anything as we're going along, then please leave me a question in the comment section down below. Alright, let's jump in. Today we're going to be looking at a multi-label classification challenge in the NLP domain. Particularly, we're going to be looking at the unhealthy comment corpus. This is a dataset of around 45,000 comments which have been manually annotated for attributes such as antagonism, hostility, and sarcasm. In this guide, we're going to break it down into 5 steps. Firstly, we're going to import and inspect the unhealthy comment corpus. We're then going to create a simple PyTorch dataset which is going to load comments from the corpus, tokenize them using the Hugging Face tokenizer. We're then going to create a simple PyTorch Lightning data module which is going to help us create our training and validation data loaders. We're then going to create a model which is going to be based off a pre-trained RoBERTa model from the Hugging Face library and a randomly initialized classification head. The classification head is going to help us classify each of our labels in the unhealthy comment corpus. Again, we're going to be using the PyTorch and the PyTorch Lightning framework. We're then going to train a model and evaluate its performance. And we're then going to compare our model to that presented in the unhealthy comment corpus paper. A Google Colab session. This is basically a Jupyter notebook hosted by Google. The great thing about Colab is that you can, if you go up to runtime, change runtime type, you can actually change your hardware accelerator to a GPU, which will massively speed up training. I've also got Colab Pro, so I can have high RAM run type, but even on the free version, you'll be able to get access to a GPU, which will massively speed up your training time. So you can go off, and once you're connected, if you actually type in NVIDIA SMI, this will actually run the command to figure out what GPU you have access to. So I've been given a Tesla P100, 16 gigabytes. So I've written out our loose plan that we've already discussed, setting up, importing the packages we need, loading the dataset, creating a PyTorch dataset, going through the PyTorch data module, and then training the model and inspecting its performance. I've created all these subheadings here so we can sort of go forward and be a bit more organized. So the first step really is going to be installing some packages that we're going to need. So what we're going to need is, so I'm going to do %% capture. This just gets rid of any of the installation dialog, which I can clutter up the screen. So we're going to use pip install, so the Python package manager, and we're going to install the transformers module. And we're also going to install the PyTorch Lightning library. I spelled that right. There we go. Okay, so that will go off and that will install both the Transformers library and the PyTorch Lightning library. In the meantime, what we can do, we can go to the unhealthy comment corpus GitHub, and let's just have a little look here. So it's called the Unhealthy Conversations by Conversation AI. Gives a rundown of what the corpus actually contains, 44,000 comments, the data, etc. So if we go to the corpus, there's a test, a training, and a validation CSV. So grab those, and you can either upload them directly into your instance, or alternatively, you can mount them in. You can mount your Google Drive and then just pull them in directly. And the reason why that's slightly preferable is that it means that if you disconnect from your runtime, you don't need to re-upload your files again. So I am going to import Google Colab, and then I'm going to import Drive. And what else do we need? that's basically, well, what we'll also do is we'll import matplotlib just for any graphs that we need. There we go. It's PLT. Right, great. So let's run that, and let's then upload or mount our drive. So mine is mounted content drive. So I'm going to do it, and then I'm going to force remount equals false. Okay, so that should go off. It should give you, permit this notebook access to your Google files, and I'm going to just allow it. They used to have this API key thing, which was rather annoying, but I think they've changed that now to this better system. So now I've mounted my drive. So what you'll be able to see now on your file browser is this drive. And in here, you can see all the things you have in your Google Drive. So I'm just going to import or write down my training path, which I've got over here. And then also my validation path. And so these are just the CSVs directly from the GitHub. So once we've just got those paths, then we can actually open them up as a pandas data frame. So I'm going to import pandas as PD, and then I am going to import them. So I'm going to go PD read CSV, and then I'm going to go train path. So that should all work. And now let's just have a quick look at what our train data contains. Right, so we have an ID for each comment. The comment is a long string of text. And then what else do we have? Well, we have these labels at the top: antagonize, condescending, dismissive, generalization, healthy, sarcastic, etc. And we have a confidence score for all of them. The confidence score, as per the paper, is basically a mixture of how many of the judges agreed on that label being true or false. The majority wins, but obviously if some disagree with one another, then the confidence score goes down. Additionally, the judges actually had a trustworthiness score as well, but I won't go too much into that detail now. So what we could also then do, so now basically we've got our data loaded. So why don't we now inspect our data? So let's just first of all, we'll go train data, and what we're going to need to actually do is copy these attributes up here. So antagonize, condescending, because we need to index into them. So I've written these all out already to save some time. So here we go. We've got antagonize, condescending, dismissive, generalization, unfair generalization, hostile, sarcastic, and unhealthy. Now we can simply index straight into the pandas data frame, and then I'm going to create a plot, which is going to be a bar plot that is going to show us, yes, so go to that in a second. So what have we got here? Well, we've got our 35,000 comments, and however many times they are positive, this adds it to the sum. So we can see that we have very few examples for things like hostility and sarcasm, basically all of the labels apart from healthy. And this is a little bit odd that they've provided the dataset like this, because it's called the unhealthy comment corpus, but they've provided healthy as the positive class, and it's the only majority class in here. So what we're actually going to do is we're going to swap around healthy to being an unhealthy attribute. So wherever it's healthy, it's now going to be negative, and unhealthy is going to be positive. So we're going to have to create a new column in our data frame called unhealthy. And this is going to be using NumPy, which we're also going to need to import. But what we're going to do is we're going to index into healthy, And then when that equals 1, as in when that's positive, we're going to make it 0. Otherwise, we're going to make it 1. So this is basically just going to flip this column. So we're going to need to do a few things here. I'll put this above here. And then I will also import numpy. So we're going to import numpy as np. Right. Let's give this another go. Aha, yeah. And we're still indexing into healthy because we've not actually done anything with the healthy column. We have just made a new column called unhealthy. So that's a little bit better. Now all of our attributes are in a much similar scale, as in we're trying to predict the minority class for all of the attributes. Remember, we have 35,000 rows of comments, and unhealthy is still our largest class, but it's still only less than 10% of the data. So now that's slightly better because when we go to look at some metrics and things like that, it's more or less on the same scale. And now we're dealing entirely with a minority classification task, and we're working with imbalanced data. Right, now let's move on to the dataset. And the dataset is quite simple. It's going to be using a PyTorch dataset, and these things are really powerful, and I'd recommend learning how to use them if you're going to be doing any sort of machine learning work at all. Get to know PyTorch a bit better, and especially this dataset class is really handy. So we're going to create a new class called the UCC dataset, and this is going to subclass the PyTorch dataset. This is how you're meant to use it. So we're going to create our own initialization function method. And what do we need? Okay, well, we're going to need a path to our data. So let's call that data path. We're going to need a tokenizer. And if you guys don't know what a tokenizer is, I'd recommend going back to my Hugging Face Basics tutorial and having a look at what the tokenizer is doing. Essentially, we're going to take the string comment, which is just text. We're going to break it up into subtokens and tokens of words, which are then actually going to be vectors. They're going to be numbers that the machine learning model that we're going to use is actually going to be able to work with. So we've got our tokenizer. And what else do we need? Well, we need our attributes that we're going to need to index into, just like we've done above. And we're going to need a max token length. And the reason why we're going to need a max token length is because everything on a batch has to be the same size. And so we need to decide how long that size is going to be. And because we know we're working with short online comments, 128 works well. The other thing that we have already seen is that we're working on an imbalanced data class problem. And so it might actually be helpful to take a sample of our majority class and then take all of our minority class, and that way we're not doing loads of needless computation when we're training our classifier. It's always better to work on a balanced data set if possible. This isn't probably the best method, and you can come up with your own solution to try and balance these classes. But now it means that we're sampling 5,000 comments from the healthy class, and we're taking all of the unhealthy comments. Well, that will be the plan anyway. Right, so let's just create all of these variables here. Right, so we've stored all of our variables. Now what we're going to do is we're going to call a private method, and we're going to prepare data. And this is going to set up the data in the format that we want. So copy this. So it's going to be a method of this class. And now we're going to have data, and this is going to read the CSV, just like we've done before as a Panda data frame, but we're going to pass in now the data path. that is passed into the class. We are then going to do exactly what we've done up here, where we're going to flip the healthy class to create an unhealthy column. Then what do we need to do? Well, if self.sample is not none, so we set it defaultly to 5,000. Realistically, we maybe should have set this defaultly to none, but the thing is that when we're training, we want to try and train on a balanced class. However, when we do our validation, we don't want to mess with the data at all. We want to leave our validation set completely untouched because that's how it's actually going to be running at inference time. So we need to see if it's actually doing any good. So we're only going to do the sampling for the training data set. So when the sample is not none, then we are going to create a subset of the data, and this is going to be where the attributes sum of the row is more than 0. So this is basically saying anything that's unhealthy is where there's any attribute that is positive. And this is why it was also useful to flip that healthy and unhealthy. So now we're going to do the same, but this is the healthy data. And this is now just going to be equal to 0. Then we can create a new variable called self.data, which is going to concatenate the unhealthy, because we want all of that, and the healthy. However, we are then going to take a sample and we're going to call in self.sample, and then we're going to make sure that every time we run this we're going to have the same, so we're going to set the random state to whatever number you like. Right, so that's what we want for our training set. However, for our validation set, what we're going to want to do is just call self.data is equal to data, because we don't want to take this unhealthy and healthy partition, as I've already explained. Right, we need 2 more methods for this dataset class. This is the length method, and this is just going to allow the dataset to figure out how large the dataset actually is, and this is just going to be equal to self.data. And then our last method, which is going to be the most interesting of the lot, is going to be called getItem. And this is going to take the index as a parameter to the method. And what this is going to do is every time the dataset is called and it wants to collect an item from the dataset, this is what's going to happen in order to get that item back. So the item is going to be self.data.index location index. Fine. However, the comment is going to be the item.comment. Pretty straightforward. The attributes are going to be the item self.attributes. So that's going to index in. And then what else do we need? Well, so we've got the comment as a string at the minute. That's just the raw text. And we also have our attributes, which is going to be just a list of 0s and 1s. What we're actually going to turn this into is a tensor of type float. And so that's now going to turn that into a tensor. So I just need to import torch up here as well. Torch. Right. So we've got the string text, but we actually also need the tokens. So in order to do that, we're going to, well, first of all, we're going to create a variable, on capitals, tokens. This is going to call the self.tokenizer, and we're going to call the encode plus method. This is going to pass in the comment in string form. And then what we're going to want to do is just make sure that we have the correct format, because by default, the encode plus method is not going to do everything we want to do. So we're going to make sure that we're going to add the special tokens, and this is going to be the beginning of sentence and end of sentence tokens. We're also going to want to return tensors, and we're going to return PyTorch tensors because we're working in PyTorch today. We're also going to truncate, so truncation equals true, truncate the comments to a maximum length. And the max length is going to simply be the self.max token length that we passed in to the class. We're also going to apply a padding token to all comments that are shorter than the maximum length. And this is going to be equal to the max length. So that's going to take the maximum length of any comment in the dataset, which will most likely be 128. Well, it will be 128. And so that means that all of our comments are going to be the same size. If they're shorter than the maximum length, they're going to be padded with padding tokens. Otherwise, they're going to be truncated and chopped off at the end. We're also going to want to return the attention mask. And this is going to be ones everywhere apart from padding tokens, where it's going to be 0. Right. So that's all the tokens that we're going to need. So we actually have pretty much everything we need. We have the tokens that are going to be returned as PyTorch tensors, and we have the attributes, which is our ones and zeros, depending on whether it's true or false for each class, and we've already returned that as a floating tensor. So all I need to do now is return a dictionary, and I'm going to return a dictionary called input IDs, and I'm going to go tokens.input IDs, and we're going to flatten those. Same for the attention mask. We're going to do exactly the same, except we are going to be calling the attention mask instead of input IDs. Attention mask. And then the last thing that we're going to do is return the labels. And this is quite simply the attributes that we've already made up here. Okay, amazing. So let's run that. That ran all okay. What do we need to do? Well, obviously, let's just give this a little test. So one of the things that we're going to need to do is pass in a tokenizer. So I'm going to, from the transformers library that we've installed, I'm going to create an auto tokenizer. And I'm going to create a model name. And today we're going to be working with RoBERTa. So I'm just going to pass in RoBERTa base for now. I'll show you something that we can do later on to actually speed up training, because RoBERTa is a gigantic model. So, but just for now, just to show you that it works, so we're going to create a tokenizer, and this is going to call the auto tokenizer from pre-train, because we want a pre-trained model, and we're going to pass in the model name. We are then going to create an unhealthy comment corpus dataset with this class that we've created up here. So let's just pass in that, and let's just pass in the training path and the tokenizer we've just created and the attributes that we specified earlier. Right. Let's just do this exactly the same, except we'll also make it for the validation dataset. Just make sure that's all working, and we'll just pass in the val path there. Okay, all right, so I've misspelled that, from pre-trained. Okay, so it's downloading the tokenizer. Right, what have I missed here? Aha, so I didn't put that in as an int, so let's try that again. Unhealthy, not in index. Yeah. Okay, so this is to do with okay. So I've spotted what's happening here. This is simply because I put in train data, but we're not working with train data, we're working with data now. Right, so let's give that another go. And this is because for our validation data set, we need to pass in sample is none, because we don't want to sample the data. Right, so now that we have fixed those little bugs, let's have a look at our items. So let's just get the first item of our training data set. Right, so this is probably just down to my poor spelling. There we go, truncation. What else do we need to do? Right, brilliant. So what have we got returned here? Well, we've got a attention mask, which is 1s for all the actual tokens and 0s for all the padding tokens. We have the input IDs, which is starts with the beginning of sentence token, ends with the end of sentence token, and yeah, that's all fine. And then it's 1s everywhere else, which is the padding token. And then we have our labels, which seems to be 0s for everything, so false for everything apart from one class, which is probably unhealthy. So let's just have a look at how large our data set is. So let's just make sure that our length function is working. Okay, so we have a length of 9,960 comments for our training data set, which we know was 35,000 originally, but now that we've taken that sample of 5,000 healthy, it means that we have 5,000 healthy and around 5,000 unhealthy comments. So that's going to do at least something to help balance the data set, and it's going to just massively speed up the training time. So now let's move on to the data module. So the data module is going to be quite simple. Probably the simplest thing that we'll be doing. It's literally going to be a standard PyTorch Lightning data module, and all it's going to do is basically return us. It's going to create our data sets for each of our training and validation data sets, and it's also going to return the data loaders for each of the data sets. So what do we need? Well, we need the data loader from PyTorch, and let's just import those. What have I misspelt here? It just needs a capital L, I believe. Great. Okay, so we're going to create a new class, and this is going to be called PyTorch Data Module, and this is going to subclass the Lightning Data Module class. Right, what do we need for our initialization function? Well, we're going to need our training path and our validation path for both of our data sets. We're going to need the attributes. We're going to need our batch size that we're going to set for our data loaders. Let's set that as a default 16 or something like that. And we're going to have a max token length again, because we need that for our dataset class that we created above. And then we also need a model name. So let's just put that defaultly as RoBERTa base, just like we did before when we created our tokenizer. So we're going to call the initialization function on the superclass. So this is going to call the PyTorch Lightning Data Module superclass initialization function. And then let's also just save all of our variables here. Okay, cool. So now that we've done that, the other thing we're going to need is to create our tokenizer. And we're going to do it exactly like how we've done it above. In fact, I'm just going to steal this. And that is going to create a tokenizer, and it's going to automatically infer which tokenizer we need from the model name. And our model name we've already passed in as RoBERTa base. So what else do we need? Well, for our PyTorch Lightning data module, we're going to need a setup function. And this is going to take a stage parameter, which is going to be defaultly none. And the setup method is basically just for the different stages of our model. So if we're predicting or if we're training. So what we need to do is if stage in none or fit, which is the training stage, then we're going to need to set up our training dataset. And this is going to be equal to basically what we've done up here. Exactly. Apart from now we need to make sure that we're passing in self.trainPath, self.tokenizer, and self.attributes. So now that we've got that, we're going to literally copy this for our validation set. So val dataset is going to be exactly the same, but we're going to pass in our training path, but everything else is going to be the same, apart from, we're not going to make that same mistake, we're going to set our sample to none. Then, what we're also going to do, because I'm going to show you guys how to actually predict from this data, from this model once we're done, is we're going to say if the stage is equal to predict, then we're going to create the val dataset, and that's it. All we need to do now is just return our data loaders. That, and so our train data loader, this is going to return a data loader, so that PyTorch data loader, and we're going to pass in our training dataset, and remember our training dataset is already of the PyTorch dataset class. Then we're going to pass in the batch size that we want for the data loader, and this is equal to self.batch size. And we're also going to want to set the number of workers, and we're going to set that to 4. And then we're also going to make sure that we're going to shuffle this. Right, fantastic. So so that's all we need to do. So this is almost done now, except we're going to need to create one for our validation and one for our predicting data loaders as well when we get to prediction time. What I'm just going to do for now is, so in practice what you'd actually do is you'd have a separate test data set, and there's a test data set provided. Just to make this as simple as possible, I'm going to keep this the validation set for our prediction class. However, yeah, it would literally be a couple more lines of code to put in the test data set. We're going to keep this all the same, except we're not going to shuffle the validation data loader or the prediction data loader, because we don't want to put any randomness or stochasticism or whatever you call it into this process when we're actually validating the model. But we can keep the number of workers equals 4, that's fine. So now let's just have a little test. So UCC data module is equal to UCC data module, and what we're going to pass in? Well, we're going to pass in our train path and our val path, which are where our actual CSVs are. And then we're also going to need to pass in the attributes, and let's see if that works. Okay, so RoBERTa base is not found. I've probably misspelt that. Aha. Yeah, I spelt it with an underscore, but it's actually a hyphen. Let's give that another go. Okay, so that's all fine. So now if I call this data module and I call the setup function, then that should create our data sets. And now if I call train data loader, then we should get back a PyTorch data loader. And this data loader can do many things. We can index into or iterate over it and get batches of data back. We can also call length on it, and this will actually return the number of batches in our in all of our training data sets. So we have 623 batches. We set the default batch size to 16, and we know we had 9,960. So 9,960 data samples. If we divide that by 16, we get 622.5. So it's filled in that extra half with some other random comments to make 623. Right, so now we've done the data module, let's actually get on to the model. So the model is going to be quite simple, probably the most complex part. Obviously this is going to be where we're actually going to be training the model. So we're going to need a few things. So from transformers, we're going to need to import the auto model, the Adam optimizer with weight decay, and the get cosine schedule with warm-up. And this is going to be our learning rate scheduler for our Adam optimizer. So just to briefly explain what this is, we have a learning rate for our optimizer. Let's see if, here they are. We have a learning rate for our optimizer, and if you have that fixed, that is not always great, because as you get further on in your training, you actually want to decrease your learning rate as you hone in on the most optimal solution. So what we're going to do with this get cosine schedule with warm-up is we're going to start from a learning rate of 0 and go up to our maximum learning rate. We're then going to decrease in this sort of cosine little slope all the way back down to 0, and this is over our epochs. So we're going to need to tell this scheduler how many epochs we have, etc., etc. And this is going to give us a much better overall performance with our model. This warm-up helps, especially with Adam, as it can be quite badly behaved at the start. So we don't want to jump around too much. So what else do we need? Well, we're going to import torch.neuralnetworks as neural networks. None. What else? We're going to import math. I believe we're going to need that. Yeah. We're also going to import torch metrics, functional, classification, import the rock score. So the area under the curve for the rock score. I won't go into this now, but this is quite a good metric for understanding how well your model is doing, especially when you have, well, it's not the best metric to use, especially for this imbalanced dataset class that we have, but it's much better than accuracy, because we already know that, you know, like 95% of our comments are healthy rather than unhealthy. So if we use accuracy, we're going to quickly get a very high accuracy, and it's not going to be very useful. So this is actually going to plot the false positive rate versus the true positive rate at different thresholds. And this is going to give us the area under that curve, and it's going to be quite a good metric, and it's what, more importantly, it's what the authors use in the original unhealthy comment corpus paper, so we can actually compare our score versus their score for this metric. So we'll do that at the end when we actually predict against the validation data set. We're also going to need to import the torch.nn functional as f, and this is just going to allow us to call f to get access to some methods that we're going to need. So let's import those. We're then going to create a new class called the unhealthy comment corpus classifier, and we're going to now have a Lightning module, which we're going to index into. So this is PyTorch Lightning module, just like the normal torch.module and n.module, but with some added benefits. So we're now going to initialize this. What do we need? Well, we're actually going to want a config file, which we're going to have as a dictionary. And this is going to include all of our hyperparameters and things. And it's going to make things a little bit neater when we're working. So we are again going to call the super initialization method. And what else are we going to do? Well, we're going to save the config. And then we're going to start creating our architecture. So we want a pre-trained model. And this is going to be equal to the auto model from pre-trained, and then we're going to index into our config, and we're going to take model name. Then we're going to return the dict equals true. Right. We are also, so now literally we could pass in a batch of our comments into this model, and we'd get back our batch after it had been passed through the RoBERTa model. However, the RoBERTa model, it's a pre-trained model that can be used for many downstream tasks. Here we're using it for classification, and therefore we're going to want to append a classification head onto the end of the model. To improve our performance even more, we're actually going to add a two-layer neural network onto the end. So we're going to have a hidden layer before we pass it to our final layer. So let's create our hidden layer, which is going to be nn.linear. And what are we going to have here? Well, we have our pre-trained model, and then we're going to index into their config and take the hidden size. And we are just going to copy this. And we're going to copy this. So we've created our hidden layer, which has input, which is the output of this, and it's going to go to the exactly same number of nodes. Here we are going to, however, index into our config, and we are going to index into the number of labels that we passed in as our hyperparameter. So here it's going to be the number of our classes, which is going to be, I think, 8. Right, what else do we need to do? Well, so we've created our hidden layer and our classification layer, but we are going to still need to initialize these layers. So we could leave them blank and Torch will automatically initialize them for us. However, if we can either use Xavier normal or Xavier uniform to initialize the weight of these neural network layers, and it's going to slightly improve our performance again. So self.classifier.weight, and we're going to need to do exactly the same for our hidden layer. Okay, so we're passing in the weights of our hidden layer and our classification layer into this Xavier uniform initialization. What else do we need? Well, we're going to need a loss function. And for our loss function, we are going to use the binary cross entropy with logits loss. And this means that we can pass in all of our output labels. So if we think it's healthy, if we think it's sarcastic, and this is going to create us a single loss that we can then backpropagate through our network and update our weights. And we're going to take the mean of all of our predictions. So obviously we have 8 classes, so we're going to get 8 losses out, or not even more than that, depending on how many our embedding size and things like that. But we're going to reduce it down to a single number using mean. other thing that we're going to want to do, so this is loss function, is create a dropout layer. And this is just to make sure that we don't overfit our model to the training data set. So what dropout does is it randomly turns on or off several nodes in our neural networks every time a training loop. So every batch, every training iteration, we're going to randomly turn off some of the nodes, and this makes sure that the model doesn't heavily rely on particular nodes or particular tokens or something like that. So it's a form of regularization. So we're going to have dropout. So that's all the initialization we need to do, but now we need to create our forward pass, which is going to be our most important thing really for our training loop. So what we're going to need is our input IDs and attention mask. We're also going to need labels, but we're not always going to need labels, so we're going to defaultly set that to none. So remember, for our training, we're going to need the labels so we can have our loss function. However, when we actually go to predict, we want this set to none, and then we're just going to pass back an empty loss. And there's other ways you could do this. You could have, there's other ways you could do this, but that's how we're going to do it. So the first thing we're going to do is we're going to have our RoBERTa model, and the output from our RoBERTa model is simply going to be self.pretrain model, and we're going to set the input IDs to input IDs and the attention mask equal to attention mask. Right, so that's passed through our RoBERTa model, and that's absolutely fine. However, the output from the RoBERTa model is going to give us an output for every single token we pass in, and our max token length is going to be 128, so it's always going to pass us back 128 tokens of output. One way we could, and this is not really useful for us, because we're trying to classify the entire sentence, the entire comment. So we're actually going to take the mean. There is another thing called the pool output or the classification output, where we take the first token, but Hugging Face suggests that we should actually use the mean output, as it's a better representation of the entire sentence. A quick little break from the tutorial to have a look at the options you have when you're designing a classification model using the Hugging Face library and one of the pre-trained models, in particular RoBERTa or BERT. It also allows us to have a little step back and have a look at what our model is exactly doing overall. Look at the architecture from start to finish. So side by side, here I have two options that we can choose upon. On the left, I have the CLS token, and on the right, I have an average or max pooling option. So let's just have a look at the similarities between these two. Well, firstly, they take a sentence. Here I put "they walked lazily." This then gets split up by one of the tokenizers into tokens. So here it's split up into "they walked las illy." This is then transformed into the input IDs, and the special tokens are appended to the start and the end. Here is the CLS, or beginning of sequence token, and here is the end of sequence token, which is 2. And in the next row, with all ones, is the attention mask. Now remember, when we're actually doing this in practice, we make sure that all of our tokens are the same size, and we add padding tokens to the actual sequence. So we'd add 1s to the bottom row for any, to get up to the maximum length. And then in the attention mask, we'd have 0s for any of the padding tokens. So once these input IDs have been found, the actual word embedding for each input ID is inputted into the Hugging Face model, or for example the RoBERTa model. This is then passed through the 12 layers, the millions of parameters, the transformer-based model from Hugging Face that has been pre-trained. Then at the end, we then pass our output of the model to a final classification layer. However, this is where the two options differ. Well, as I already mentioned, we get output for each of our input tokens. On the left, what we do is we discard all the tokens apart from the beginning of sequence or the CLS token. When we actually go to training time, this CLS token is then relied upon to learn a representation of the entire sentence, and therefore we can actually get quite good output from a single token. The other option is to use an average or a max pooling layer, where you take the outputs of all of the RoBERTa tokens for all of your sequence, and then you just take the mean or you take the max, and then you get another representation over the entire sentence. This is the second option that we're going to go for today, and this is what's recommended by Hugging Face. However, in practice, I've tried them, and they always seem to be quite similar. But this has given us the opportunity to actually look at what we're doing. And then, obviously, in this final classification layer, as we've already looked at, we've set up a hidden layer and a classification layer for each one of our output labels, such as sarcasm or hostility. So now let's go back to the tutorial and finish setting up the model. So that's what we're going to do. We're going to call torch.mean, and then we're going to call our output, and we're going to take the last hidden state. And the dimension that we're going to take the mean on is going to be the first dimension, which is going to be the tokens that we have. So that's going to give us back the pooled output. And then we are going to then pass this through into our neural network layer. So neural network classification layers. So what do we need here? Well, let's just keep this pooled output, and we're going to pass this first into our dropout. So this is going to enforce the model to, even with some of the tokens missing, it's going to force the model to try and classify the sentence with only a few of the tokens left. Although, actually, let's not do that yet. Let's instead, let's pass it through the hidden layer first. So self.hidden. And then we're going to call the dropout layer. So self.dropout. And then we are going to pass this through an activation function. So we've already passed in functional. We're going to call the ReLU activation function, which is the most popular activation function by far. And so this has now gone through our first hidden layer and some dropout. So then what do we need to do? Well, we're going to pass it into our final classification layer. So we're going to call self.classifier, and then we're going to pass in this pooled output. Right, so now we've got our final output of the model. So now we can calculate the loss. So our loss is going to be initially 0, but if the labels is not none, then we're going to create our loss, and our loss is going to be equal to the self.loss function. And then we're going to take our logits, and we're going to make sure that they are the same shape. So we are going to transform that to that shape, and then we're going to do exactly the same with our labels that we know have been passed in because we've got this if statement. Then we're then going to return the loss and the logits. The logits is just the fancy name for the output of our model, of our final model. Except, of course, this is a classification challenge, so we're actually going to be wanting to pass our output through a sigmoid function to make sure that it's between 0 and 1. However, we are going to have this, we're going to be using this binary cross entropy with logits loss, which is more stable. So this loss combines a sigmoid layer and the binary cross entropy loss in a single one class. This is more numerically stable than a plain sigmoid followed by the binary cross entropy loss. So we're actually going to be passing back these raw logits. without the sigmoid function applied. Right, now we need to create our training step, and these, and our validation step and our prediction step. And this is going to be what the model does at each step of our training. So our training, our validation, our prediction steps. These are quite straightforward. We're going to have a batch of data that's passed in from our data loaders and the batch index. And that's not quite right. Right. So what's this going to do? Well, we're going to get our loss and our logits, and that is just equal to our self, and then we're going to unpack the dictionary. And remember, we're going to get back this dictionary that we've created up here, attention mask, input IDs, and labels. We're just going to unpack that directly into the self. And because this is inheriting from the NN module from PyTorch, this is going to call forward pass. So we're going to get our loss and our logits back. We're then going to call self.log, and we're going to save our train loss, and this is going to be equal to our loss, and we're going to set the progress bar equals to true and logger equal to true. Right, and then we're going to return our loss, our predictions, and our labels. Okay, amazing. So now we're going to copy this, and it's going to be very similar, except it's going to be the validation step and the predict step. And they're going to be almost identical, except this is called validation loss, and this is going to be val loss. But apart from that, everything else is the same. For the prediction step, it's going to be slightly different, because we're not going to care about our loss, our loss, yeah, that's correct. We only care about our outputs, because that's what we want returned. So we're actually just going to return our logits. And that is almost done. So we've almost got our entire model. The only thing we have left to do is to configure our optimizers. And this is going to be quite straightforward. Going to be a little bit of work we're going to need to do, but it's mainly just setting things up. So we're going to call our adam.w from the transformer library. This is going to work on our parameters of our model. And then we're going to set the learning rate is equal to the self.config learning rate. And we're going to have a weight decay, and this is going to equal to self.config w decay. Okay, so that's our optimizer. We're now going to need to set up our scheduler. So our scheduler is going to be pretty straightforward, but we're going to need a few parameters first. So we're going to need our total steps, which is going to be equal to self.config train size, because obviously this is going to be for training. And this is going to be divided by our batch size. Config batch size. What else do we need? Well, let me just close this parentheses. That's everything. Am I missing something out? No. Right. We're also going to need to calculate our warm-up steps, because remember we have a warm-up period for our learning rate scheduler. This is where we're going to have the math and we're just going to floor our total steps times by some percentage. So we're going to pass that percentage in. I'm just going to call that warm up. So now we have the warm up steps and the total amount of steps, then we can now actually create our scheduler. And this is equals get cosine schedule with warm up. What's this going to have? Well, we're going to pass in our Atom optimizer into this, as well as our warm up steps and our total steps. And that is it. And then we're just going to return a list of our optimizers and a list of our schedulers, which we only have one of each. Right, so optimizer, and what else we're going to spell warm-up steps. Okay, right, so I think that is good to go. So let's just give it a go. So let's pass in our config. So we're almost there now. We almost have everything we need to train. So what do we need for our config? Well, we need to pass in a model name. And here's the thing that I was going to mention earlier is that, so although RoBERTa is great, it is a very large model. So the people at Hugging Face have also created a distilled version of the model with way less weights. It's not as good. So if inference time is not something you care about and you're only after performance, then use the original model. But just for this tutorial, I thought I'd show you this. So we're going to use distill RoBERTa base, which is going to be smaller, faster to train. And we're going to be using, well, we need to pass in our labels, which is just going to be the length of our attributes that we'd already created. What else do we need? Well, we need our batch size. And our batch size, let's just create it as 128. You may need to adjust this depending on which GPU you can get your hands on. We're going to start off with a learning rate, which is quite small. So, but this is within the standard range that the people in the RoBERTa paper recommend. And then we're going to set our warm-up percentage. So we know that this needs to be a percentage, so let's just set this as 20% of the total number of steps. We also need to pass in our training size, and this is going to be equal to the length of our data module dot train data loader. Okay, fantastic. And then we have our weight decay. And let's set this to something quite small as well, something like 001. Getting some commas here. And final thing is the number of epochs that we need to train for. So let's just set this as 100. And now that we've created our config, and I prefer having this config outside and we can sort of automatically adjust it. There's lots of other ways we can optimize this, especially if you're doing hyperparameter tuning. This is, you don't want this config hardwired into your model. You want to be passing this config in. And if you guys are interested in hyperparameter tuning, we can do another thing on that with something like RayTune, maybe using a model like this. So we have our model here, and this is going to be equal to our classifier, UCC, what do we call it? UCC classifier. And all we need for that is our config. Let's see if that works. And whilst we're waiting for that to load, and hopefully it won't break, but it does. So it has no thing called hidden. Aha, yeah. Because I didn't even put equal signs, put minus signs, because I'm a weirdo. There we go. Let's give that a go. Okay. Has no thing called classifier. Okay, I've called it classification. So I've probably called it classifier here. Yeah. Right, let's give that another go. Okay, so that seems like it's worked. So in order to make sure that it's definitely working, what we can do is we'd already created this dataset class. So let's just pass in an item from our data set. So we're going to want the input IDs, and we are going to want the attention mask, and the labels. So these are the three things that we need in order to get a prediction and a loss back from our model. So I'm just going to call the model onto the CPU. Well, let's just see if this works. So loss output is equal to model that we've created up there. And let's just pass in input IDs. And we're going to need to unsqueeze this because our model at the minute is expecting a batch of data. But because we've called our, I should have really called the data loader class, but we are going to need to add an extra dimension on here because we're only getting one sample back. So we're going to need to do this for our attention mask as well. Attention mask. And we're also going to need to do it for our labels. I didn't call it attention mask, I call it am. Okay. So let's just see if, okay, so, and this is why it's useful to do. I've misspelled this to views, but it's just view. Okay, amazing. So now let's just see what our loss and our output looks like. Amazing. So we've got a loss back of 0.85, and we also have got back a list of tensors, or has 8 values, 1, 2, 3, 4, 5, 6, 7, 8, 1 for each of our classes. So these are actually our raw predictions for each of our classes. So now we know that we can pass in some raw data into our model. So now we're actually in a position to train. So let's create our data module. So let's just copy everything from up here. We'd already done this, but it's just nice to have it all in one place. So we have our UCC data module, but this time we're going to be passing in batch size. Batch size is equal to config batch size. And we're going to call setup, just like we've done previously. And this is going to create the correct data set that we're going to need. We're then going to call model, and we are just going to do exactly what we've done up here. Again, we're not doing anything new here, we're just getting everything into the right frame, into the right cell, so we can look at it all in one. So now we're going to train. So in order to train, we're going to be using a PyTorch Lightning trainer. And the PyTorch Lightning trainer is simply going to take the config, number of epochs, and it's also going to take the number of GPUs that we want, which is the one great thing about PyTorch Lightning is if you have multi-GPUs, it will do it for you automatically. I've not done that before, but apparently it's rather good. And then we're going to set the number of sanity validation steps. And this is useful as well because when you, let's say a training epoch takes a long time, and you get all the way to your validation set, and you go all the way through the validation step, and then something breaks in the validation set because you set up your validation step slightly wrong or something like that. You don't want to get all the way through your training, which is normally the majority of your data, and then for it to break at the end. So this just makes sure, does a little sanity check at the beginning to make sure that you've got everything in the right order. So let's just set that to 50. And then we're just going to call trainer.fit, and we are going to pass in our model and our data module, and that is it. So this will go off, And so let's have a look. Some weights of the model checkpoint were not used when initializing the RoBERTa model. This is expected if you're initializing a RoBERTa model from a checkpoint of a model trained on another task, which is exactly what we have. We have a pre-trained model, and now we're retraining it with our classification head. So that's just a warning to make sure that we know that. We then have GPU available true, which is great because that's what we want. We want our model to be trained on the GPU. It's being used. And then we actually have our training. So we have 82.1 million parameters for our pre-trained RoBERTa model. We then have two layers, a hidden layer and a classification layer. Our classification layer has 590,000 weights. Our final layer has 6.2 thousand weights. And then we have our loss function and our dropout, which obviously don't have any parameters. And we are actually going to get a loss and our training loss, and it's going to go through our epochs and it's going to be training. So obviously this is going to take a little while. I've set it to 100 epochs. You could set it to significantly less. We'll have a look at how it does at the end. So I'll come back when this is all trained and we can have a look at the model. Okay guys, so I've come back and I've done a few things. So I'm just going to run you through everything that I've done. So firstly, I've called in the tensor board and I've loaded the Lightning logs, which is going to load the logs that we created in our training and our validation steps. So you can have a little look here at our validation loss over the epochs and our training loss over the epochs. So our training loss looks like it was constantly going down. Our validation loss, on the other hand, seems to have plateaued and seems to have slightly gone up again, which would say to me that our model is slightly overfitting on the training data and it's not generalizing to unseen data. However, we have a model and it looks like it has learned at least something. So let's have a look. So I've also created a few other little things and I'm predicting with the model that we've just created. So I've created this really simple class called classifier raw comments. It takes a model and a data module and predicts the prediction data set. This is what yes, the prediction step and the prediction data set that we passed in, which remember we set to the validation data set. And again, you'd use a test data set. In reality, I'm just doing it here for simplicity. And if we were fine-tuning or something, you definitely wouldn't want to do this because you could fine-tune on your validation data set and that wouldn't generalize to other unseen data. So all we're going to use here is NumPy to stack these up and we're going to get these flattened predictions out. We're then going to pass in our validation data set and we're going to get the true comments, the true labels, the ground truth data. And then I'm just going to create a simple, so we're going to import sklearn and we're going to get the ROC curve and the ROC AUC score, and we're just going to plot the same graph that was seen in the actual paper for the unhealthy comment corpus. And let's just have a look at our results compared to theirs. So here is the exact same graph that we have, that we've created. And as you can see, so this paper, they use the BERT model. And I had a look at that implementation, and there was a few things that would have changed. For example, they're using stochastic gradient descent instead of Adam. They're not using a learning rate scheduler. A whole bunch of things that they could have changed. But this paper wasn't about the model, it was about the dataset. So it was always going to be improved upon. But we can see that for pretty much all the labels, we are actually getting better results. So, for example, sarcastic, which they note in the paper as being particularly bad, they get 58 here, which is slightly better than chance. We're now getting 75 for sarcastic, which is great. Generalization. So for unfair generalization, we're getting 88 RoC AC score. Here they get 67. And things like hostile, they get 82. I think we get something very similar, 82. So, you know, and that sort of maybe makes sense that RoBERTa is slightly, it's gets better results on all data sets. It's better trained. It maybe has been trained so much that it can pick up on slightly more nuanced attributes such as sarcasm and unhealthy conversation. So yeah, that's what we've done today, guys. We've created a model from scratch using a data set that has not got much online material for. It's newly released, came out last year, and we've improved upon the baseline. We've loaded it up as a PyTorch dataset and a PyTorch Lightning data module. We've created our model and we've got some good results out. So these aren't perfect. If you were to analyze these results even further, you know that this is still a really, really difficult task. It's very subjective, but we have got better results than the baseline, which is quite exciting. And hopefully you've learned some things along the way. So let me know if you've enjoyed this tutorial, and thanks for watching.